In this video, we're going to be finding the real zeros of a polynomial. So we need to establish a couple of things before we do this problem. So the first is that the number of real zeros, I'm just going to write the number of zeros, is at most equal to the degree of the polynomial. So if we look at this example above, it says find all zeros of f of x equals negative 2x to the fourth power plus 2 times x squared, so that the number of zeros is at most equal to 4. So that doesn't tell us what our zeros are, and that doesn't tell us how many zeros there are. There could be 4, there could be 3, 2, 1, or 0, with some caveats in there, but there certainly cannot be 5. So that is point number 1. And, well, you know what, let me take the time actually to remind everybody here what a zero is, right? So let's just say, let's do an example. Say we have a polynomial, and we know that x equals 3 for a given polynomial. Okay, let's just remind ourselves what that means, okay? That means x equals 3 is a zero of the function. Okay, so oftentimes we refer to that as a zero of the function. X equals 3 is a solution to the equation f of x is equal to 0, meaning if we set the polynomial equal to 0 and solve it, we would find that x equals 3 is a solution. We also know that if x equals 3 for a given polynomial, then x minus 3 is a factor of the polynomial. And finally, if x equals 3, then 3 comma 0 is an x-intercept. So you may remember back when we were looking at linear equations, I made a note that zeros and x-intercepts and roots, which I didn't use here, but all of those are kind of used interchangeably because all of this information is packed into this small statement, x equals 3. Okay, so that's just a reminder of what the zeros are. So let's look at this example, and let's do the first part, which is asking us to find all of the zeros. So we're going to start off by factoring this polynomial. Well, I'm going to set it equal to 0. That's actually step 1. Set it equal to 0. So now I'm going to solve this, and I'm going to solve it by factoring. So I can see that both of these terms have a 2 in common. I'm going to take the negative 2 out because the leading term is negative. I just kind of like to incorporate that negative with the leading term. So now if I divide everything by negative 2x squared, I'm left with x squared minus 1. Now I can continue to factor that. I can see that the leftovers here are a difference of 2 squares. So the greatest common factor is going to come down, and I can factor the rest as a difference of 2 squares. And now the rest of my factors are prime. I should say the remaining factors are prime. I can't factor this anymore. Now I can use ZPP. So I set each factor equal to 0, and then I solve. So this first equation, x is going to be equal to 0. You could go through the steps of that, but it's pretty obvious that x has to be 0 there. I'm going to subtract 1 on both sides, so x is equal to -1. And then I'm going to add 1 to both sides here, so x is equal to 1. So one thing I want to make a note of here is this equation here. Well, you know what, let me actually solve this first equation. I said x is 0, but let's actually do this, because there's something important that's going to be here. So I'm going to divide both sides by -2. So I get x squared is equal to 0. Then I take the square root, and we get x is equal to positive or -0, which we know is just 0. So notice here, this is what's called a double root. Okay, I'm getting two answers here that happen to both be 0. Positive 0 and -0, which are both 0. So when we count up our zeros, I'm actually going to count this one twice. So we have 1, 2, 3, 4 zeros. Okay, so even though when we list our answers, we have 0, -1, and 1, 0 is a double root. And that's where we get our 4 roots out of this equation. Okay, now the next part of the question asks us to determine the maximum possible number of turning points of the graph of the function. So turning points is another word for relative maximum or minimums. Okay, so we've seen this in a past video. And the number of turning points is equal to, at most, the degree minus 1. So if you have a polynomial that has a degree of 5, it has at most 4 turning points. If you have a polynomial that has a degree of 1, you have at most 0 turning points. That would be a linear equation. So in this particular case, our example on the left side, we already know that it has a degree of 4. So the maximum number of turning points is going to be 1 minus 4. I should say 4 minus 1, which is 3. And if we were to actually graph this, let's see what we get here. I'm in Desmos right now. It is a very handy tool. And we could see, kind of zoom in, and you can see that we got 3 bumps. So the graph on the left is increasing, and then it's decreasing. So we have a turning point that is at negative 0.707, comma 0.5. That's decreasing, and then it starts to increase at the origin. That's our second turning point. And then it's increasing, and then turns and starts to decrease at 0.707, comma 0.5. So we have on our graph 3 turning points. And that is how you find the real zeros of a polynomial and the maximum number of turning points.